Guys, I started recording some lessons here and there and putting them on YouTube, and although I didn't want to, I've just bitten the bullet and made it public. Okay? So if you Google Mr. Bayes, you'll find my YouTube channel, which has got really boring mathematical lessons. Okay? Don't do it right now. I'll know if you do it right now because you'll burst out laughing. I said, don't do it now. What's the matter with you?
Mr. Bayes, you're going to be the new Khan Academy.
Yeah.
Mr. Bayes, math.
It's like your profile picture. Why are you the Hulk?
Because I'm angry. Haven't you seen this? Sharon, can you hear me?
Yes.
Yeah. Okay, so what I'm going to do, if your internet is terrible, just you can go and do something else. Look, I will post this on internet and I'll leave it there for about over the weekend, and you can just either download it or watch it a couple of times and then just let it go, and then I'll take it down on Monday. Okay?
Yeah.
All right. Sweet. Okay. Now, for the rest of you.
We're up to 7 subscribers, Mr. Bayes.
Woohoo! Okay. Right. You know, it's going to be negative exponential growth for the subscribers to my YouTube channel. All right. Now, so where the thing is here with extension 1, what we're talking about is the rate of change. It's always about the rate. Exponential growth and decay revolves around the idea of rate being proportional to how much there is. Okay? The more there is, the greater the rate of growth. Okay? So if you can imagine a normal everyday exponential curve, right? Let's just say like this here. This is the 2 unit. I'll call this AO, A. You've already got this. So, and then I'll say A is equal to AOE to the KT because it's growth. Now think about the rate. Now the rate is the rate of change of the population. So let's call that the population over time. Let's call that time, not X. When I do that, AO is a constant. That becomes K E to the KT, dA dt, K A0 E to the KT. But this, we know, is A. So therefore, dA dt K A. Now, you notice it's positive. Now the rate is positive, which means it's got to have a gradient that is positive. It's increasing. Now, what this basically says is, the more people there are, the higher the change, the higher the rate of growth is going to be. So, I might mute you all, and then you can unmute yourself with the space button if you need it, okay? Because I'm getting this weird feedback sound. Right, so the rate of change here and the rate of change here and the rate of change here, you can see is constantly changing. It's getting faster. The rate of increase is getting faster as time goes by and as the population is increasing. So this was the rate of change. That's the gradient at that population. That's the rate of change at that population. That's the rate of change at that population. And you can see how the more people there are, the greater the rate of change. And it works in the exact way for negative. With a negative gradient, you would get something that looks like this.
How did you go from the second last line of like working to the last line?
From here to here, because this was my graph. Yeah? See this here? In the box?
Yeah.
That's
Oh, I see. Yeah. Okay.
this. Okay? Now this here is this. That's AO, that's A, that's T. And in exactly the same way, we would do exactly the same thing, but we would get this. Now again, this is the gradient. That's the gradient. That's the gradient. That's the gradient. And you can see, now it's the exact opposite. As time increases, the population decreases. And when the population decreases, the rate of change also decreases. And it has a negative gradient. But that's all 2 unit. But we know that if we have an exponential, you know, well, when you have an exponential curve, you differentiate it, you get another exponential curve. So you can actually write the derivative as a version of the original curve. And this is the definition of exponential growth. But that's 2 unit. And that's quite simple. Now, my question to you before I move on from here is, if I told you that, let's do this one here. If I told you that dA dt is equal to Ka, can you see that? Then it would be true, now wait for it, that this is the case. Is that all right? Because I just took the inverse of both sides. Now, here's the good thing. What about if I integrate both of these with respect to A? So A is my variable. Well, the derivative of t with respect to A, integrating with respect to A, that's just t.
Is there an equal sign in the middle?
Here, here.
Okay, it's great. It's good work.
Because this is just the derivative. If I integrate the derivative, I just get back to my original. K is a constant, isn't it? So I could move that constant out here. What would this be? What is the integral with respect to A of 1 on A?
Log A?
Log A. See, if you ignore the fact that it's A, and if I was to ask you this question, everybody would give me the answer. Oh, that's log X. I know that. I know that. It's exactly the same thing here, but with A. So this now becomes this. Which now becomes this.
Is that not just cos C?
Yeah, well, I'm just showing you the decay there. That would be a new constant. If you don't want it to call it KC, you could call it a new constant. I don't know. Big C. Doesn't matter. But it's a constant, right? That's the important bit. So that would mean that log A is equal to KT plus some constant C. Dumb. Some constant C. Oh, you can do minus, it doesn't matter. Because a constant's just a constant. It's never going to change. That would mean that A is going to be equal to E to the KT minus C. A would be equal to E to the KT times E to the minus C. This is just a constant. If I let E to the minus C equal to A0,
Wait, what does that line say? Is it just A equals to E? The up. Is that just A equals to E?
A is equal to E to the power of KT minus C.
Okay, I see that. Yeah. I thought they were just separate lines. Okay.
In the second last line where you just said let E.
Well, this is some constant. See this here? This never changes, whatever the hell this is.
Yeah.
So it turns out that that is my initial amount.
What are we doing? Like, what did we just do?
We just went backwards.
We're just proving it.
Yeah, we just went from the derivative to the actual population itself. So if I have this and I differentiate this, I can get this. But if I have this, I can integrate it and get my original population. So I can go forwards and backwards, differentiation and integration. Now the reason I point this out is because with the extension 1 topics in particular, they don't tend to give you the equation, they tend to give you the rate. And you're meant to prove that the equation is this. So you have to do this integration part.
So the rates,
The rate is, that's the rate. The rate is always the derivative. And if I integrate the rate, I get my original formula or for my equation for whatever we're measuring, in this case A. So you can, if I have this, I could differentiate this and do that. I think we did that right at the beginning. Or if I have my rate, notice how I flipped it, I integrated it, and then just did the algebra and eventually got back to my equation for A. That's the rate of change of A. That's how quickly A is changing over time. This is how much A there is at any given time. Whatever A is. A could be the population of a country. A could be the number of bacteria cells in a sample. It could be anything. The number of foxes. It could be anything. This is how many foxes there are. This is how quickly the number of foxes is increasing. So they're very different. Sometimes you're given the equation for the number of foxes And then you asked, how quickly is it increasing? Sometimes though, in the harder questions and more extension questions, you're given the rate, how quickly something is increasing, and then they say, how many foxes are there? So you've got to go back and find the original equation. The other thing about the extension is that now they put another transformation into your exponential, right? Who remembers this? So, am I okay to rub this out? Good. Who remembers this? What would it be like if I asked you to graph this? Now, that's a constant. That's just some constant P. Now, an exponential curve has this shape. The fact that I have, I should call this A0. A0 normally would mean that the y-intercept, where I start, is A0, but not in this case, is it? In this case, at time equals 0, my y-intercept is going to be P plus A0. And then it's going to start up. And it's going to look like this. That's just a constant. That's time. See how we had our normal curve and we just lifted it up by a factor of P. You know, that's quite useless. Right? What does that tell me? That as time approaches infinity, the population is going to approach infinity. Well, big deal. Where the interesting thing is when this happens. Look. Now that's pretty cool. What's going to happen there? What's that going to look like? Well, the minus in front of the t, that means that transformation-wise it's going to flip this way. Because the positive x's or the positive t's are now going to be negative t's, and the negative t's are now going to be positive t's. And everything flips around from my normal one, and everything still gets moved up by p. So now my graph is going to look like this. A, that's going to be some number p. This is going to be p plus a0. Okay, that's where we are. And then look at what happens.
Oh.
Now, that doesn't go to 0. Instead, it goes to a specific value, p. So, I'll give you an example of the sort of thing that this measures. Okay? I want you to think about this. I want you to think that, hang on, I'm just going to